Hello everyone, July 24th again. Alright, this time we're going to do for today. Yeah, I think doing this in the morning is not going to work. Alright, so this is the one. Find first and last position of element in sorted array. Given an array of integers, nums, sorted in non-decreasing order, find the starting and ending position of a given target value. What do you mean by starting and ending position? Is not found, return this. It must route in all log and runtime complexity. So the starting and end is 0, 1, 2, 3, and 4. Okay? 6 doesn't find, 0 doesn't find. Which I think if we want to do 10, it should give me the same thing, right? So let's say return, I just return 0. I just want to make sure. If I want to find 10, that should give us 5, 5. Huh? Oh. Well, they check this type. Alright, so how about let's say 5 and 5. Yep. So it's non-decreasing. Oh, two binary such, right? If I do, hold on, let's do it this way. Can it's a 22, and that's at 23. That's what 20 is that 22? Yeah, let's call that 22, and then so today this will be 23. It's all messed up. It's all messed up. I think we missed one day. That's the thing. We missed one. It's supposed to be only 1 day in difference. Actually, no. I don't want that. I want it to be. I want this to be 23. So then we can do today the 24. We just missed 1 day. Just fine. Well, the least resistance, right? That's what we're trying to do. We have a right and a bisect left. And then we just return. Oh, we have to say index il index left shall equal to bisect left nums target, right? And then we say if because it will always go to the left, so we just say if nums this is not equal to target, then we're just going to return false, right? Otherwise, we're going to return this and then bisect right nums target. So this one shall be -1 because this will put there, so we're going to -1. Okay. So let's try this. I'm going to use the, and we can actually keep using this example. It's such a good example. We can do 5, we can do 7, we can do 10. Right? We hit almost all different cases. What is that? Oh, why you return false? Why? Sometimes, no, I don't understand myself. I just return false. Alright, so we have some issue. Hold on. Empty. Empty. Alright, so I say if not nums, return -1, -1. Yep. Oh, wow, back then I used CPP. Oh! The heck? The heck is this? 2 and 2. What's bisect left? Oh, shoot. Yeah. So I just say if this is equal to, oh yeah, if it doesn't exist, is if it's not the 1, or if it's bigger. So if this equal to len nums, or edge case. I'm pretty sure last time I hit on this edge case as well. Maybe we should hit another edge case. Like, I don't know, 2, 2, let's say 1. Right, on the one on the left, one on the right. On the left, this shall solve. Okay. So 2 binary search. Is that 35? Oh, what was this method? Did I not use? Huh. I think I just tried to write binary search myself. These days I don't have this in me. Okay, so we done this. Now we're gonna go work on this one, which we barely passed using BIT. Alright, so this one, it says we're going to merge, so we'll have to go back to the problem itself. Count the number smaller, okay. And we use BIT, barely passed it, and BIT passed it. And we have a bunch of time mix. Jeez. Okay. Merge sort. Give an example, okay? So we'll split and split. We merge 5 and 2. We take the smaller one, put the smaller element into the merged area. Yes. 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 Okay. And as we merge, we'll prepare the first, so we know 1. Because this is always to the right of this, so when we merge, 1 is always to the right of 2. So when I compare, we can increment 2, and also increment 5. Yeah, because when I compare, 1 is smaller, so if 1 is smaller, yes. So when you merge, we'll find a smaller one. So 1 will go first, and that's from the right side, right? If that's from the right side, that means everybody on the left side will increment by 1. And then this comes. So every time this comes up, we can count how many from the right has already gone. So every time this comes up, I increment. And then this comes up, I increment. And then I do this. Oh. Holy guacamole. My God, this is smart. My God, this is smart. Very, very, very smart. All right, let's try to code it ourselves. This is some next level stuff. Simple problems sometimes. What the hell, man? What are you doing? Come on. Come on. Yo, this is a good problem. This is such a good problem. Wait, do I have test cases for this? Yes, I think I do. Okay. This is a really, really smart solution. Use merge sort. Since at each level, we always merge the left half and the right half. So naturally, if a 1, so naturally all the smaller values on the right half can count towards the result of the values on the left half that are bigger. And merge sort already does the comparison for us. All we need to do is to keep track of the count of the values on the right that are smaller. Okay, so merge sort. We can do this. Dang, we can do this recursively, right? Yeah, it is. Merge sort is recursive. So we can have a result. Now, how do we have the result? That is a good question. Well, the implementation I need some more thinking about implementation. So we skip a split in two, and eventually we come to 2, and then we have a left and have a right, and that's how we merge. And when we merge the 2, so we will say merge sort. We split in 2, and then we say merge left, merge right, and we will return a merged list. Yes, we'll return a merged list, which is fine. We'll return a merged list. And split in half, we will just call it when we call, we only need to pass in indices. So we pass indices. Okay, indices, and then the final is going to be this, and that will return 0. That will return, and that will just return. We have to keep track. So we have to have a result, right? And then once we sort them, we have to have the indices associated with them. If we don't have indices associated with them, we don't know where they are, right? Like because eventually everything will be sorted. So this thing, when we want to count how many is smaller, right? Let's say this one is smaller, so we count as 1, right? The smaller is 1. And then when this one comes in, we have to increment. So what we need to do is to have a new nums that has the index associated with the value. So when we see the value, we know the index. Okay, so here is the result, right? So the rest, we say n equals to n nums, and now we say result is going to be this times n, and we're going to redo nums. So we say nums equals to ni for in enumerate. Wow, amazing. Nums. Okay, then we're gonna say def merge sort. What do we need for merge sort? We need the indices, right? So when we say range left and the range right, okay. Let's call low and high. Low and high, and we don't return. We do have to return things. We have to return the list. Okay, so low and high, we say if low equal to high, then we're gonna return nums. What do we return? That's a good and we just return this thing. All right, we return the two things. It's a tuple. We return a tuple. Otherwise, we're gonna say mid equal to and low plus high divided by 2. And then we say sorted left equal to merge sort low and mid, and sorted right, let's do it in one line, equals to merge sort mid plus 1 and high. Okay, so as we do, we need to merge these two. Okay, and then we have the count called C, count is 0, and we're gonna merge these two. Right? How do we merge? We have 2 pointers, right? 2 pointers. So we're gonna say I and j. Okay, I equals j equals 0. Okay, and we have, no, we don't have. We just say while I is smaller to len sl and j is smaller to len sr, right? What do we say? We're gonna have a result, right? And the result. Yeah, res is equal to this, okay? And we're gonna say if SLI, let's say if this one is smaller, what if equal? Equal doesn't count. We have to be small. How many is smaller than you on the right. So if it's equal, we will just push. We'll just push left first. Okay, if it's equal, we'll just push left. So that means we won't trigger a count. So we say if it's smaller or equal to sorted right, then res.append this I, 0. Okay, then we append this and nothing changes, right? Else, if the left is larger than the right, then we need to append srj and I plus equal 1 and then j plus equal 1. But in addition, actually we have to do something here, my bad. So every time we append a left, we have to also record. We can also say res. So we need to say R. Okay, let's call it R because res is a global. Okay, so we say res. So we append SLI. So SLI1 plus equal to C. So how many that's small? How many on the right smaller than this is already being added? That's basically what it is. And this is going to be C plus equal 1 because at this point, right? At this point, we say the right thing goes in. The right thing is smaller, so count how many as smaller as already go in. And then whenever we left goes in, we can, yes, that should be right. So blah, 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 once we're all done. And then we have to check. We say if I is smaller than ln SL, right? Then we need to push, right? Actually, it's just going to be while. I'm going to say r dot append SL I plus equal 1, and then we repeat this thing. Right, we'll repeat this thing. If it's on the right side, that's smaller. Okay, if it's on the right side, that is smaller. Then we just simply append them, but don't change anything. Right, we just say while j smaller than sr, we just say r dot append srj j plus equal 1. Okay, once we're done, we return r. So we're just going to do merge sort of 0 and n minus 1. And once we're done, we're going to return res. All right, let's see. Solution 2, does it work? Nope, not at the moment. What happened? List index out of range. That is interesting. How? Oh, of course. Of course. What are you doing, man? You cannot increment and then it had to happen before. This has to happen before we pass. Okay, so 164. Okay, so oh no, we have one more. Okay, actually, this is O and login. Ooh, O and login. So good. So good. It's one of the few really smart method I've seen here. So screw the BIT, right? Screw the BIT, screw the segment tree, even though both can work. We have some huge thing. Is this one we hit a huge thing, right? Yeah, let's try the huge thing. I don't have it here, but yes, this is a huge thing. Lordy, this is huge. This is a couple thousand. Okay. Let's see how fast you can handle this. I think 1,000 milliseconds. Then we're good. Ooh, 1,000 milliseconds. All right, let's try. 1,000 milliseconds. We will pass. It's actually faster. It's faster than a little bit faster than BIT. Gordy is such a good solution. Such a good solution. All right, so this one's down. I call it done. Call it done. This is a good one. What number is this? 315. 315. I put it in my nightmare, but this is actually a good one. Can I just hard it? Yeah, I should hard it. This is a good one. That's a really good one. Simple problem. Very simple problem, but interesting. All right, so this freaking thing that's been bugging me for so long. Okay, so here's the idea. We saw the hints, right? The hints basically tell us it has to be something DP, right? yeah, it says you want to calculate the current one based on something before, but it's more of a prefix sum, right? So here's the idea. So we have this 1, 3, 1, 2, okay? Now, if we want to calculate the contribution of all the subarrays that ending at, let's say ending at 2, right? Then it's going to be 1, 2, 3, 1, 2, 1, 3, 1, 2, right? That's all. So we need to know the sum of them, but at the same time, we also need to know which one we shall base it on, the smallest value that we shall base it on. So that means we need to have a monotonic array in it, because in monotonic array, when you look to your left, everything is smaller than you, right? So if you want to extend to the left, so these guys on the left are going to be the base for everything. So now the problem becomes how to deal with all the values that gets popped, right? All the value that gets popped. So imagine there's some value in between 1 and 2, right? So it's going to be 1, 3, 1, blah, 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 and then 2. And then 2 is smaller than every blah, 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 blah. Any help? Is smaller than any blah, blah, blah that's in between. So when 2 comes, I'm going to kick out all of them. But as we're kicking all of them, what we notice is everything in here, all the subarray, that's starting from anything in between, that's bigger, ending at 2, they are all going to be based on 2, right? You know what? Yeah, I think it'll be better if I do this. So yeah, it'll help me clear my mind as well. Let's say we have 5, 6, 4, 7, 5. It doesn't matter, right? So we don't care about how these things go. We just care when 2 hits, right? What we know is if it's a monotonic array, 5, 7, 4, 6, 5, all these will be kicked out, okay? And then we'll end at 1. So as we kick them out, we know 5, 2, 7, 5, 2, 4, 7, 5, just too many. This should be enough. 4, 7, 5, 2, all of these subarrays have the same base. Now the base is 2. So it's going to be a 2, of course, by itself, and 5 plus 2 times 2. 7 plus 5 plus 2 times 2. 4 plus 7 plus 5 plus 2 times 2. So if I know the sum of all of these things, right, like 5, 5, 7, 5, 7, 4, if I know all of these, then it'll be very easy for me to calculate this everything, like all these things, okay? So now the question is, how can we find the sum of 5, 5, 7, 5, 7, 4? How can I do that? So what we can do to find the sum of this, actually we can actually include in 2. Right? Actually it's a 2, 2, 2, 2, 5, and 2, 5, 7, 2. Yeah, that's all right. We don't have to include 2. So what we want to find is 5, 7, 5, and 4, 7, 5. We need to know the sum of these things. So to know the sum of that, what we can say is if at that point we need to have a prefix sum, okay? A prefix sum. Prefix sum of what? You know what? This is actually might not be a good. Let me fix this. Let's do 4, 5, 7. So we don't have any popping along the way. We know 7, right? That's the thing. We know 7. So from 7, we know that at this point we have 7 times 7, right? The contribution of 7 is 7 times 7, 5 plus 7 times 5, 4 plus 5 plus 7 times 4, right? This is what we know at the moment. Man, I had it. Hold on. I kind of lost it. How does this logic work? Well, it works. The contribution at 7 is this. The contribution at 5. What's the contribution at 5? It's 5 times 5. And 4 plus 5 times 5. Right. And then, what's your contribution to 4? 4 is going to be 4 times 4, right? And what we want to know is 5, 7 plus 5, and 4 plus 7 plus 5. That's what we want to know. We have a 4 plus 7 plus 5. Man, don't do this. Don't do this to me. I had this. Come on, man. I had this. Let me think. Then how do we find the sum of... What was the method I was thinking on the other day? I have a method. Come on, I have a method. I have a method. Come on. You have a method. We can do 3, 3, 1, and 3, 1, 4. If we go reverse style, right? If I have something as 2, right? 7, 2, 5, 7, 2, 4, 5, 7, 2, and 1, 4, 5, 7, 2. Okay? If I build a prefix sum like this, then I can get 5, 7, 2 plus 4, 5, 7, 2 plus 1, 4, 5, 7, 2. Actually, I don't need 4, 5, 7, 2. So we have 4, 5, 7, 2 plus 5, 7, 2 plus 7, 2 plus 2. We have that if we go from right to left, right? And then we use this. If we minus 2 times 4, that's what we get. Oh, that's what we have is 7, right? And we get is 7, 5, 7, 4, 5, 7. Yes, that's the first level of prefix sum. So if we want to find anything, right, then we go from right to left. Right, we go from right to left. We pre-build this prefix sum, and all we do is from this index, right? So if we want to find this, we find this index. Right, we find this index minus this index, okay? This index minus this index, and we need to minus So what if it's like this, right? That's going to be this index minus this index. So we will end up at 45772, 14572, 314572, right? And we need to minus 5 plus 7 plus 2 times 3. Then we get this, right? Then we get this. So that's the first level, okay? That's the first level we can get. So this is the level when we pop. And every time we pop, it is guaranteed that these are sorted, right? These are sorted, so you can just pop them out. But hold on, that's not what we had, because you might have something else. You know what? No, I don't think this is the method we got the last time that we thought about this problem. Man, I should have solved the problem that day when I had the idea. Now it's kind of escaping me. No, I don't think that's the one. We have to rely on the previous computed contributions from these, right? Otherwise, it's impossible. The previous computed contribution. Oh, hold on. Scratch everything. That's not the way to go. I remember it's from 1. It's from 1. That's the thing. It's from 1. Okay, hold on. So whatever we're gonna pop, I don't care. I don't care what we pop. What I care about is after we pop, we'll end up with something that's smaller than me, right? If I end up with something that's smaller than me, which means everything in between is smaller than me, is bigger than me, right? Which means I just need to find their base. And it just so happens that before me, their base is going to be 1, right? All of their base, like the 7 base is 1, 5 base is 1, 4 base. So 1, 4, yeah, we have to go this way. 1, 4, 1, 4, 5, and 1, 4, 5, 7. They are all based on 1. And with this, we don't have to worry about things gets popped in between. Okay. But what does that mean? That means we find all the values that's in between. We don't care. We can find all the values, right? The original values. And they will be all... Oh yeah, isn't that what you did? That's exactly what you just did. No, it's still valid. So we don't care about the exact values here. What we care about is the indices between these two. Yes, that's the one. The indices between these two. That's what we care about. So when we given something that's smaller, right, then we have the index between these two. And then everything in these two, we want to find their sum, the sum I just described, which we can compute, okay? Which we can compute. We can pre-compute it, okay? So that thing we can get done. And once we find that, and the contribution for 2 is just all of these, because this plus, and then they're gonna plus 2 times the whole number, because we have to add 2 to it, and then whole thing times 2, because that's 2 is basically their base. Okay, so we get rid of all these. Yes, that's how we done with the things in the middle. I gotta do something.
They both finished? They both finished?
The morning? One of them has just a little bit.
Oh, Jimbo.
Yeah. You want to try Fancy Fast?
Fancy Fast plus leftover?
Okay, give the leftover to Jumbo.
Why?
We can give the leftover to Jumbo. I think it should be fun because because there's only a little bit of food and we can always cover it with dry food.
Then you don't get much dry food.
And I feel like I gave too much dry food to Jimbo because he has been eating it during the day.
Huh?
I feel he's a bit chubby. A chubby boy. Jimbo, this is Fancy Fest. I haven't given you Fancy Fest since you were a kitten. I haven't given him Fancy Fest since he's a kid, but you showed no interest in Fancy Fest, absolutely. Therefore, this is going to be an adventure. Oh, no, 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 no.
Chopper.
Like I said, she doesn't make a meow sound. She makes a sound.
Dirty. Milk and blueberries.
Quite much more to do for.
It's moving me hard.
I deal with Jimbo, don't worry. Oh, you smell marvelous. Oh, your hair looks marvelous. Come on. Come on. Come. I put dry food down and he's eating the dry food. He's trying his best not to touch the wet. John. 1. Jim almost finished. I am surprised. To say the least. Good boy. All right, let's do a few more. So we figured out the first part, right? Now we're going to figure out the second part. Is from this, okay? So now what we need to know is from this, because everything to the left is going to be smaller. Like this doesn't exist. Everything to the left is smaller than me. So what I want to do is to know, because what we see is a list of sorted, but in between there are going to be some values. So I want to say everything here towards this, right? And they have to also extend towards this. Right, and then they have to all times this. Can we do that? We can do that, right? So it's just gonna be whatever plus 2 plus whatever, right? So it's just gonna be this. No, he finished. So what I want to know is this to this, right? And this to this, this to this, and this to this. Actually, it's this to this, this to this, this to this, this to this, and they all multiply by this thing. How do I know that? Well, isn't that the same? Right? That's the same thing. Which we have this. Basically, it's just almost there. This plus this plus this plus this minus from so this towards the end. Oh, I have to repeat myself a little bit. This towards from this to this, all of these. So we have all of these minus all of these, and then we get it, right? Then we get it. So basically, what we're saying is, if it's basically this range.
Actually, I don't want this.
think she starts to realize food is plenty.
Why?
She doesn't have to eat everything and all the time.
She practically finished.
Yeah, she does finish, so it's fun.
Why?
Smell like cat food.
Thanks for hanging.
It work? Is it dry?
Okay.
Uh-huh.
I don't know how to do okay.
You give it to me, I'll dry it. Give it to me. You do your thing. Oh, fun.
You see, you said that earlier. I don't do one more
It's dry. It's dry. Some dryer. Technique. No, I think it'll be fun. Come on. I think it'll be fun. I love it. That would be fantastic. Like black with like red on both sides. Like your car. Like my car. I like my car in the case. My phone case. But the phone case is red with black. I like black with red. Come on. He's in the neighborhood watch. Come on. Come. Come on. Come. Come on. Come on. Come on. Alright, back. Oh, it's already been 1 hour. I said I had it, but I still don't have it. We have the leverage, whatever this one has. Alright, let's see, what do we have on this one? What we have is on this, right? We have this, this, this. We can solve between the new one and this one. Right, this we have already solved. Now from A2, we basically then is something like this, this, this times A2. And then we have this, 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 times A3. Times A4. Do we want to stay inside? Right, so what we want now is alright, I'm gonna end it here. I have to keep thinking about this. I'll see you guys tomorrow. Adios.